Thank you.
Thank you. Yeah, thank you. So let me just share my screen. So today I wanted to talk about cosmological structure formation. So I was asked to talk about this topic. So if you remember, on Monday I talked about the lambda CDM model in terms of defining what it is, defining its main ingredients and the key principles behind it, and also basically giving lots of observational evidence, or some of observational evidence that support this picture of an effective model, effective in the sense that with some parameters and ingredients that doesn't explain, is able to, it takes them and is able to explain structure formation in the early universe and also in the late universe. So what I will do today is to discuss some topics on precisely more the theory behind this model, what actually structure formation is, because I didn't really cover that. It was more about the topics on providing the basis for the ingredients and observations. So what I will do is to divide the talk roughly in three, although the first part is the one that dominates, which corresponds to what is known as linear perturbation theory, which is the part that deals with the growth of perturbations as they are very small. So basically just shortly after the time of inflation until the time of the CMB and a little bit beyond that. So as the name implies, it means that we are dealing with fluctuations over a mean average that remain small, roughly until maybe 10% or so, when perturbation theory is still valid. Then after that, I will talk more about what is known as the nonlinear regime. So what happens when the perturbation becomes larger, but I will not cover that too much because I know that tomorrow there's going to be a session on n-body simulations, and it is n-body simulations that cover this regime. So I will not give too many details. Instead, I will concentrate on, at the end of the talk, on talking about deviations from the lambda CDM model for structure formation, because I think they are quite relevant and quite timely, because they remain open, and these are models that are also very interesting when it comes to particle physics. So I will discuss that in the last part of the talk. Okay, so let me start then. So as I said, I'm going to start with this linear theory of cosmological perturbations, and I will go into certain detail here, but the idea is just to give you the main physics behind this, and not to do the derivations of the equations or anything like that, just to give you at least a feeling of where those equations come from and what physics do they imply. So we saw this picture on Monday, and of course you know it very well, is the cosmic microwave background radiation. From this picture, we basically have as I said, all the ingredients from the lambda CDM model. So the amount of matter in the universe, the fact that the universe is flat, the expansion, Hubble parameters. So all of these ingredients that go into the lambda CDM model can be extracted from this picture. So they, in some sense, all of those ingredients, global ingredients, govern the expansion of the universe, as I said, also on Monday, through the Friedmann equation. So you can know how the universe is going to expand, knowing its matter content. But we also, from this picture, know that the universe, this was 400,000 years after the Big Bang, the universe was not completely homogeneous. It had these small perturbations around, as I put here, 1 in 100,000. So very tiny fluctuations in the temperature, which are basically the same thing as the perturbations in the density. Not exactly the same thing, because we are seeing the photons. We are not seeing directly the matter. But there is a relatively straightforward factor here between the perturbations in the fluctuations in the density and the fluctuation in the density and the fluctuations in the photons. It's a factor of 3. So this picture gives us a statistical representation of the level of fluctuations that we expect, and they are the seeds of all cosmic structures. So they are the seeds that will become eventually galaxies and clusters of galaxies and so on. So how do you tackle this challenge of saying you have this system statistically, and then you have this as initial conditions, and then afterwards you can imagine, okay, what is going to happen to both the dark matter and the gas, the ordinary matter, so dark matter and the ordinary matter that is present here. So to do that, you need to solve some equations, right? So you need to know that, well, what is going to happen? Well, it's going to be gravity, right? So gravity is going to be one of the force. And at least for dark matter, that's it. It's just gravity. If we stick to the CDM model, because the CDM model would give this hypothesis that at least when it comes to structure formation, we don't have to worry about anything else at the level of galactic structure formation. So gravity is the only interaction that matters for dark matter. But of course, when it comes to ordinary matter, so if a gas, well, as I discussed earlier, is going to feel also, of course, the pressure, the radiation pressure, and so on. So there are other at least pressure, right? So you have gravity and radiation pressure, or even if it's not, if it's not radiation pressure, because that was a mistake, because the photons are already decoupled after the CMB, not before. You have to take into account these two regimes. So a regime in which they are coupled to the photons, and a regime in which they are not, but they still have collisions, right? Ordinary matter has collisions. So the general way to deal with this is what is called the Boltzmann equation. So I wanted to start with the Boltzmann equation because I think sometimes it's an equation that is actually not given at all at the certainly not at the undergraduate level, and in many cases not even at the graduate level. It becomes specific in physics. I mean, it becomes specific to certain fields where I think it should be. It's a fundamental equation. So this equation relates what is known as the phase space distribution. It's just this F is just the number of particles that you have of a certain species. Say, for example, let's talk about dark matter first, located in position and in phase space at a certain time. So this is position, momentum, time. And what this equation is telling us is that the change of this phase space density or phase space distribution, it has different names, can change in time only if there is collisions. So if there is exchange of energy either internally through collisions between the particles themselves, so if the system is collisional, or if it collides with, or if it interacts with other particles. So this operator here is called the collisional operator. I'm not going to go in any detail at all, but it just tells us, the level of contact interactions between the particles. And in some sense, here is where the particle physics enters. Whereas in this part, it talks about the global general evolution that has to do with, for example, long-range external forces, like, for example, it could be electric fields, global electric fields, or of course gravity in our case. So if you put this collisional term equal to 0, so if the species is completely decoupled, for example, dark matter, then this collisional term is 0, and then you get this equation, which is a collisionless Boltzmann equation. It's also called, it's related to what is known the Liouville's theorem in classical mechanics. So I'm not going to go into detail, but basically the point is you have a 0 here, and this derivative on time is called the Liouville's operator, and it just basically splits the derivative with partial derivative. So you have something that depends on time, and then you have a gradient in real space and in momentum space. So you transform that equation, the Boltzmann equation is transformed in the case of gravity into what is known as the Blasov-Poisson equation. So you start with this equation here, and then you just expand the operators. And because we are dealing with gravity, you introduce the gravitational potential. So that's going to be related to the derivatives of the in position with respect to time. And you know that this potential here, the potential that enters here, the one responsible from the forces, so the dp dt that enters here, this potential is caused itself by the distribution of matter that we have. So this is why it's called self-gravity. So the density of, say, keep on talking about dark matter because it's a collisionless example in the case of CDM, then the density of matter generates this potential. So it enters into the Boltzmann equation. So the evolution of the phase space distribution, it doesn't change globally, right, as a function of time. It can be modified, but it can be stretched and so on, but the phase space density cannot change. But here is where the potential enters. So this equation is basically the equation we will need to solve to tackle the question of what happens to the dark matter if you have certain initial conditions and it's completely decoupled from everything else. Then you would just solve this equation in principle, right? You would solve this equation with the initial conditions, and then it will tell you the evolution in time for a given point in space and momentum. It will give you the whole complete information. But of course, it's a very difficult equation to solve because it's for each particle, for each point in space, it has, at a given time, it has 6 dimensions, right? In x, 3 in x, 3 in momentum, and of course on time. So instead, we deal, or usually what is done, is to make average quantities, so to make like macroscopic averages. And so this is what basically statistical mechanics does. So it takes this kind of, say, approach, and when you do kinetic theory, for example, then you do these averages, and then you make this thermodynamic approach or statistical mechanics approach. So I'm not gonna, as I said, go into too much detail. Just to emphasize, this is the key equation. And then you make an average, as I said, to say, okay, what is gonna happen to an average quantity that I'm interested on? For example, what is this average quantity? Well, it could be the density, it could be the mass, it could be the momentum, it could be energy. So all of these thermodynamic quantities. And these thermodynamic quantities are just averages over the phase space distribution, because the phase space distribution gives you the probability of the particle being in momentum or in phase space at a given time. So if you know how many particles you have in a certain patch of phase space, then you can compute everything. So, sorry, is there a question? No, yes, just please feel free to stop me and ask questions if you have any. So these averages are called moments or expectation values. As I say, something that is done in statistical mechanics. But as you will see very soon, it's basically the beginning of cosmological perturbation theory, and actually the beginning of very famous equations that perhaps you haven't seen, or some of you haven't seen, connected to the Boltzmann equation. So this is why I kind of took the time, I wanted to take the time to show you this, because I think it's very important. So when you take these averages, which consist of making, for example, you want an average in position, so you want to know what is the average, say, kinetic energy or momentum at this position, then you just do the integral over momentum. Anyway, so this is just a detail, so I'm not gonna stop in this. But the point is that you can transform this Blasov-Poisson equation, which governs the evolution of the collisionless system, you can transform it into what is known as the master moment equation, which is an equation for these moments, Q, which I haven't said exactly what they are. It can be anything that has this macroscopic average. So you basically have the same ingredients as the collisionless Boltzmann equation, a partial derivative, a gradient in space, and here it enters the potential in a gradient in momentum space. But the advantage of this equation is that you don't have to deal with the full Boltzmann equation. Instead, you deal with these averages. And what is the advantage? Well, you can show that the first two moments, one would be the mass, that would be what is called the first moment. So you put it here Q, you put just the mass of the particle, then you get an equation for the density, the mass density. If you put the momentum, then you get an equation for the evolution of momentum, as we will see in a second. But before doing that, let me just make the other important comment. So I talk about the collisionless Boltzmann equation, so that's dark matter. So what about ordinary matter? So let's say a fluid that has collisions. So the gas that is, think about the CMB. What do you have at the moment of the CMB? You have ordinary matter. So basically neutral hydrogen. And then you have dark matter. And this neutral hydrogen, of course, is going to have collisions. Let's say it's like air in this room. So you cannot set this set of the Boltzmann equation equal to 0 because you have this this possibility of collision. And as I said, this part of the Boltzmann equation is what governs, these local interactions between these particles, the collisions between the particles. So this is it becomes a much more complicated equation. And the collisional Boltzmann equation is, for example, used to compute the abundance of dark matter species, as you probably have seen already, and many other things that had to do with the particle physics here, not only of dark matter, of course, but of other particle species. But the nice things about the very nice thing about the master moment equation is that under certain conditions, you don't have to worry about this term at all. Because when you do this average, you have these conservation laws that apply to the average. So if the collisions are contact, so that means, short range, you can put a box around the collision. They are elastic, and something else that is molecular chaos that I'm not going to discuss. Then the 0 first and second moment of the equations are the same as the collisionless case. So in other words, the collisional part drops out and you don't have to worry about it. And this is because mass, momentum, kinetic energy are conserved, which are these three first moments, the 0 first and second moment. So these assumptions is what is known as the fluid regime of the Boltzmann equation. So I took the time to do this to basically arrive to this slide. So this was the thing I wanted to start with. So you have this master moment equation that comes from the Boltzmann equation. And what is surprising to me, at least the first time I saw it, because nobody explained to me when I was a student, I never saw this, but I thought it's a very fundamental equation precisely because of this. From this equation, you can talk about collisionless systems that dark matter, like dark matter, and then you derive the moments of the equations, just the first two, so the 0 and first. You get what you have seen, and for sure all of you, are known as the continuity equation, which is the conservation of mass. It tells you just how the density evolves. If you take the first moment, so if you take Q equal to the momentum, then you get this equation here that maybe not all of you have seen. It's called the Jeans equation. But you probably have seen the equivalent for fluids that I'm going to discuss in a moment. So let me take this aside for a moment. Then you still have the Poisson equation, which is just gravity. So you have 5 equations for different variables that have to do, this U has to do with the velocity of the particle, the density, and so on. And I'm going to talk about this sigma later on. But the thing is that you can also talk about fluids. So this is a collisionless system, dark matter, and this is a fluid, ordinary, say, baryons. Under these conditions, then you get basically the same equations, but the interpretation is different. You get a continuity equation, so this is the same as this one. And now this is the famous one that you have seen, which is the Euler equation. So this is the Euler equation that you see in fluid mechanics. Here you have the potential, you have the pressure, and these, usually you see it, for example, in the equation of hydrostatic equilibrium, then you have these terms equal to zero, because you have a steady state, an equilibrium state. But this is just the Euler equation for the fluid, and this U represents the bulk motion, the velocity, the average velocity of the fluid, like in parcels, so how it moves. It's simply fluid mechanics without viscosity. It all comes from the same equation, the Boltzmann equation. In the case of dark matter, what you notice is that the term that is different really is just this one. But it's not so different, you just have the rho sigma square. You have to just make the connection with the pressure. And this is because in the case of a collisionless system, you do not have a pressure, but you have something else, which is the random motion of the particles. So maybe you remember on Monday when I talk about the galaxy clusters and how they are held together against gravity by the motion of the galaxies. This is basically a galaxy cluster is a collisionless system when it comes to the galaxies, right? The galaxies, the probability of the galaxies colliding is very small. So when you have a collisionless system, what plays the role of the pressure in some sense is this rho sigma square, where sigma is the velocity dispersion. So it gives you these random motions, give you the support. So I just wanted to show you that why the Boltzmann equation is so important. So we are going to be talking about these equations, and you see, because they are so similar, you can basically talk about one of them, one set, for example, the fluid, and just make the replacement of sigma squared with the pressure. So let me stop here for a moment and see if there are any questions so far. No?
Do you hear me?
Sorry, yes, I hear you. Although I hear a lot of echo, so I don't.
I have a question.
Okay. I hear.
Maybe my microphone is. So
now I hear you. I hear you much better.
Do you hear me?
Yes. Yeah, I hear you fine. So go ahead.
Okay. So my basic question is, okay, in the first case, the collisionless case, you got discontinuity, the first equation, the continuity equation. In order to get that, what did you set for?
Yes. So so this is a good question, because I didn't go through this, but you have this equation which comes from the Boltzmann equation, and then you have to set this Q is an average, and in principle, it can be any average quantity that you want. You are basically making a statistical average or thermodynamic average. So if you set Q equal to the mass of the particle, so for example, to the mass of dark matter, you set Q equal to M, then that's just a number, right? So you don't even need to make an average, because the average of the mass is always the mass. And then you put, because we are talking about the mass of the particle, and then you see just M times N, and N is the number density, so you get this first term.
Yes, and the last term is 0, of course.
The last term is 0 because it's yes, the mass doesn't change.
Okay. Thank you.
Oh, you're welcome. So we have these equations, and this is basically the starting point. And as you see, it's not just a starting point from cosmological perturbation theory, it's the starting point for any analysis of either collisionless system or fluids, right? Because these are the fundamental equations for fluids. In the case of the, the no viscosity, actually with viscosity, you also you get an extra term here, which is called the Navier-Stokes equation. So everything comes from the Boltzmann equation, either fluids or collision systems. Now, let's go back to the topic, which is to actually talk about perturbation theory. Now, to do this properly, to do perturbation theory, we're talking about a universe that is expanding and very large scales. So in principle, you have to use general relativity, but you don't need to understand most of the properties. You can just go along or understand pretty much all of the physics except for a few exceptions by talking about Newtonian physics. So it's much easier. And this is what I'm going to do, again, just to sketch what is it that you have to do. And the first step is to go to a comoving frame. So you take the expansion of the universe and remove it from your frame of reference. And this just makes it easier. Instead of always talking about coordinates that are suffering from the expansion, then you just, I talk about comoving coordinates in the first lecture, but essentially you put all the expansion into this scale factor. You have comoving positions that are always related to the physical positions by just this scale factor. But in the comoving frame, you just talk about what happens aside the expansion. So for example, if you have gravitational instabilities, which is what we're going to have, or gravitational forces that have nothing to do, so you have the expansion of the universe is expanding, but for example, you have a bit of a clump of dark matter here and a clump of dark matter, so they are going to start attracting each other. And that would go into the comoving description, because the universe is expanding, but in the comoving frame, all of the frame sees is the gravitational attraction. So this can be done for the position, and of course for the momentum, you just take the derivatives, and then you have two terms. One of them we have already seen, which is just the Hubble expansion. So this first part governs the expansion of the universe. So this is the Hubble expansion, and we talked about it already. And then there is a second part, which, as I said, deal with the local motions, which are called peculiar velocities. That's just the name of this second part. Okay, so there's one for the expansion and another one for everything else that has to do with that doesn't have to do with the expansion. Now, this system of equations that are here, for example, now concentrate just on the fluid. You cannot solve the system of equation because you have five equations, but 6 variables. 5 because this is 1, 2, and you have 3 for this, because these are vectors. So you have 5 equations, but you have 6 variables: the density, the potential, the pressure, and the 3 components of the velocity of the bulk motion. So you need another equation to solve the system. That equation, in the case of fluids, is, or also in the collisionless case, you need an equation of state. So the equation of state, again, this is thermodynamics, right? So you're dealing with average quantities, so the pressure, density, for example, and temperature. And for an ideal gas, well, we all know the equation for the ideal gas. But you can write the equation of the ideal gas not in terms of the standard, PV equals rho T, or NT, sorry. You can instead write it as an equation of the density and the entropy. This is very convenient in perturbation theory, because if you do this, then you can assign the, as I put here, there can be the pressure gradients connected to density gradients and entropy gradients. What is an entropy gradient? Is nothing more than heat exchange. So if you have heat exchange between the particles, you can put it into this equation. Makes you see it more easily than using the temperature. So that's just a detail. So once you do that, then you arrive into this set equation. So these are again the continuity, Euler, and Poisson equations, but now written in terms of the comoving coordinates and using the equation of state. So again, this is just a conservation of mass. And here I have changed the density. I should have put here, I forgot a slide here, but the density is just going to be given by the density of the background and a perturbation, which is this delta here. So this is the delta, the perturbation over the background. So this equation transformed the continuity conservation of mass is just an equation that now depends on, we are talking about this perturbation over the background, the peculiar velocities. Then you have the continuity equation that instead of just this bulk motion, we're talking about the peculiar velocity, which is still an average, it's still a statistical. We're not talking about a single particle that has a single motion, it's the whole ensemble of particles. You have the potential and the pressure term, so the pressure gradient here that enters into the Euler equation, as I said, is transformed into a term that depends on the variations of the density and entropy. Here it enters the sound speed. So here's where the sound speed comes about. There's a question. The question says that if you have a system that at some time, how do you evolve with time? S equals 0. So you mean S, by S you mean entropy? I suppose yes. Okay. Yes. So the entropy cannot be 0, right? Because the entropy is you have basically the second law of thermodynamics, right? At the beginning, you have low entropy, and that entropy just continues increasing. So the entropy cannot be 0 because it's a measure of the number of configuration states of the statistical or thermodynamic system. So, for example, you have gas in this room, and it has a certain temperature, but the number of possibilities or microstates, as they are called, or rearrangements of the particles in this room to give you the same temperature is extremely large, and that arrangement has to do with entropy. So the entropy cannot be 0 because the arrangement cannot. Sorry? Okay, there is one. Yeah, so in the CMB, you have a system that is basically in thermal equilibrium before. So the CMB is the time when basically this system decouples. So you are talking about, I think what you're trying to say is what happens if the system is in thermal equilibrium. If the system is in thermal equilibrium, then you know the solutions for the distribution function, and then you know everything. So for example, if the gas is classical, then the distribution function is a Maxwell-Boltzmann distribution, and it has a single temperature associated to it and a pressure and so on. There is no variations. There is no deviations from being homogeneous and so on. If the gas is, it can be a Fermi-Dirac distribution or a Bose-Einstein distribution if you're talking about a quantum system. So if the system is in equilibrium, we know F, right? That doesn't depend on time. Here we are talking about something that is going to depend on time because you have deviations over this equilibrium configuration, okay? Which are driven essentially by these two things, okay? I hope that answers the questions. So what we have here is essentially the seeds or the sources of this pressure in a fluid. It could be density. Okay, you have the sound speed, so basically these sound waves, right, that I was talking about. But you could also have heat exchange that is connected to this entropy. Now let's get rid of the heat exchange, because the idea is, this is sometimes called in the perturbation language or in the cosmological perturbation theory as adiabatic or isentropic. So adiabatic, there's no heat exchange. Isentropic, the same entropy everywhere. So you don't have this possibility of heat exchange. And the idea is that if you think that the primordial perturbations have this property of not having a primordial seed for entropy, or so for entropy gradient or heat exchange, but rather just simply different densities across, then this is the case that is generally or more generally discussed. But of course, there is the other possibility as well. So I will just stick with this one. And then just basically just a bit summarize, and I'm going to just get into the main equation that describes a perturbation theory. So now we have all these equations, and now all I have to do is linearize them. So these equations are completely general, so rho can take, as I said, it could be is the background plus a perturbation, but I haven't put this perturbation language into the equations. I haven't said that this delta is very small compared to rho. So I haven't done this. Delta is, see, I didn't even define it, I should have. Delta is just the density minus the average divided by the average. So it's the relative density of at any given point. So if it was exactly homogeneous, delta would be 0. If it's very small, as we know from the CMB, it's just much smaller than 1. And then these equations can be simplified. And that's really what the perturbation, the name perturbation theory comes from, because you are going to reduce these equations to make this change. Also means that the expansion, the physical expansion of the universe is much more, so the physical velocity caused by the expansion is much larger than any velocity that you have caused by the gravitational instability or by the pressure, by the gradients in the pressure. So once you do all that, then these equations become much simpler, and then you can combine them. You can combine them into a single equation. So a second order differential equation for the perturbation. And here is where all the physics is about. So in some sense, the last half an hour, a bit more, has been just to reach this point, to show you, at least to give you a glance of how come this equation comes about. I just didn't want to put it there and tell you this is the equation. So the equation really comes from the Boltzmann equation, very beginning. And if you want, okay, go to a bit lower level, continuity, Euler, and Poisson. You combine them, you linearize them, and you get this second order differential equation. So it tells you basically how the perturbation is going to grow. So again, now let me just try to make like a summary. This delta is the deviation, if you want, over the homogeneous background universe. And this equation tells you how this delta is going to grow as a function of time. And it has some terms. So first is a term that has an h here. This is called the Hubble drag term. And you see it's positive. So this term, because of where it is in the equation and the sign it has, you can just see by that, and you know, of course, that because the Hubble, this h, which is the Hubble expansion rate, well, what it's doing is expanding, is making the universe expand. So it's going to make perturbations grow more slowly because the universe is expanding. Then you have this term here, which is positive on the right-hand side. And this is the one related to the Poisson equation. So this is the one that, basically the gravitational growth. So here the perturbation is going to grow because of gravity. Then you have another term that has to do with this pressure gradient. How the sound speed is the remnant of this gradient of the pressure. This is just essentially pressure caused by collisions at the very, from the very start between the particles in the fluid. And the nice thing about, I hope, the introduction I gave is that I don't have to, I hope, convince you too much, because it's the same set of equations for a fluid and for a collisionless system. They are basically looking the same. The only thing you have to do is replace something. There is no sound for a collisionless system because there are no collisions. So the sound speed shouldn't enter here at all. It doesn't have a meaning for a collisionless system. So instead of the sound speed, you just replace it by the velocity dispersion of the particles. So for dark matter, you just take this equation and you replace by sigma squared. And that's the same equation that you have to use. Whereas for fluid baryons, you just take the sound speed. That's it. So that's why it's, I think, so nice to see this connection with the Boltzmann equation, which is the fundamental equation. So you can use it for both cases. Okay, so what this equation is telling us, so just one last step. This equation is you know, this is basically delta in real space. It's an equation in real space. And what you do to solve it actually is to go to Fourier space. And the reason you do that is, well, it's just much simpler because the deltas, the gradients, so sorry, the Laplace operator becomes just an algebraic k squared. So the equation is much simpler, right? If you see this equation, it looks scary because you have this one. But once you look this equation, it looks much more easier because you just have this k here. It has, there are other reasons behind this. It has to do with the universe being periodic, so you can do your Fourier analysis because you have this periodicity. Why is the universe periodic? Because of the cosmological principle. Periodic statistically at very large scales, you can take a patch of the universe and treat it as the same as another patch because of this periodicity. But the physics is essentially the same, right? So you have a term related to gravitational growth, you have a term that is gonna counteract, which is the pressure, and then you have another term that is related to the expansion of the universe. So just to comment, each k here, so you have basically a system now of equations for each k. So what represents a k? And you can think of the k as representing essentially a scale, a perturbation of a certain scale. So you say, okay, I'm going to talk about perturbations of a given physical size, and that represents this k in Fourier space. The larger the size, the smaller the k, and vice versa. And you can take different scales as evolving independently. Again, this is just a relatively small detail, but I will just concentrate on the physics of this equation. So let's talk about the fluid case. Let me just check the time. And let me stop here to see if there are questions. No. So as I said, I want to talk about the physics of these equations. And let me start with the, is there a question?
What? Yes.
Sorry, can you repeat?
What about the initial conditions for to solve this equation?
Yes, that's
the initial condition. Do you hear me?
Yes, I hear you. I hear you. So the initial condition, yes. So this, yeah. So that's a very good question. I mean, you have to take the initial condition comes from. So for example, the delta. I guess the easiest way to describe this is you start probably with velocities that are around zero. So the peculiar velocity is one of the things that you have to put. And the other one, delta, can come from, in general, you put it equal to the prediction from inflation. Once you talk about all the models coupled, so the inflation gives you the term for basically the. I need to reach this other part, but it essentially tells you the amplitude of the fluctuations, so which is the thing that is going to enter here. Of course, you can start in principle with a delta equal to 0, eta equals 0, because it starts very homogeneous, or an arbitrary low number, and you're still gonna get the right answer. Okay, because it grows quickly, so it's not very sensitive to that.
So it is supposed that we are going. The initial condition is going to be set in the beginning of the universe at the inflationary epoch.
Yeah, in principle, yes, but
I mean, we want to follow this delta k, which depends on the time. So
yes, so in principle, yes.
Yeah, I'm concerned a little bit about this because, for instance, we said that all the perturbations, or this delta is going to be much less than 1.
Yeah. So, sorry, I cannot hear you anymore.
Yeah. The thing is that, for instance, in some epochs of the history of
Sorry, let me let me stop you, because I really can you
in which intuitively I would think that
I cannot hear you. I cannot hear you.
Perturbations cannot be as small as to assume an intuition. I don't know if that is. Yeah. I mean, what happened in the years that can.
Okay, yeah, because sorry, I couldn't hear you. So maybe if you can type the question here in the chat, and I will try to answer it. But I suppose the question was related to while you write it. Okay, yeah, I'll do that. So write the question in the chat, and I will try to answer it later. Okay, so let me just continue and say that the fluid clay, so the baryonic perturbations, right? So what can I say about the physics of this? So we have this equation here, and just to concentrate on some of the physics that are behind it, if I set this term to 0 for the moment, so if I talk about just the Hubble expansion here, set it to 0, then I just concentrate on this interplay between pressure and gravity. So when that happens, you can see in this equation directly, right? There is going to be a game between gravity and pressure that governs the evolution of the perturbations. And actually, this equation is very well known. It's called the wave equation. It's just with this W being the difference between these two terms. And it sets a scale in the system, which is called the Jeans scale, because it separates two regimes depending on W square being positive or negative. So it's called the Jeans length, and it's connected to what I talked about earlier, the sun horizon scale and so on Monday. But for now, it doesn't really matter the actual value, of course, in detail. Just there has to be a physical scale, because it depends on which one wins, and you can understand physically this very well, very easily, right? If, for example, if W square is larger than 0, then it means that the pressure term is kind of winning, or is more important. And then what you have in the solution, you can just solve it very easily. So for modes or for scales of the system, so for perturbations that are smaller than this Jeans scale, so if you have very small perturbations, then what happens is you have this oscillatory behavior. It is these acoustic oscillations that I talk about. Here's basically the equation for that. So gravity and pressure are supporting or balancing each other and keep the perturbation from growing. It just doesn't grow anymore. Okay. So this is the case that is stable. So it's called Jeans stable. And this is where the sound waves idea comes from that I described also earlier. Now, in the other case, if W squared is negative, then what happens is the perturbation is too large. Then it essentially means that the pressure cannot stop gravity. So it starts trying to oscillate, but gravity wins. And it means that the delta is going to grow. So the solutions are exponential, and if the number is imaginary, then you have these oscillatory solutions, as in the previous case. And if it's real, then if it's imaginary W, then this becomes real, and then you have an exponential growth. So that means that the perturbation grows exponentially. Right? And this is what leads to gravitational collapse and to the form, or let's say the beginning of structure formation. So for perturbations to grow, the perturbation has to be larger than the Jeans scale. Okay, so I'm going quickly here because I already talked about the acoustic oscillations. So, okay, so then you have these two possibilities for a fluid, acoustic oscillations or unstable modes. And this Jeans scale is important because it sets the difference between perturbations. If they are too small, then they just oscillate. If they are too large, then they can grow and collapse gravitationally. So you have something like this. Now, this is just a scale, but this scale is going to depend on where you are in the universe, at which time you are. And here, this is just a sketch, just super quick, just to tell you, just by looking at this equation, depends on the background density, on the sound speed, and the scale factor. So all of these are evolving as a function of time because the universe as a whole is expanding and is changing. Is changing what? Is changing which components dominate the global universe. If it's radiation, like at the beginning of the universe, then it has a scaling with the scale factor that is different than if it's matter, and so on. And also, the sound speed of the fluid itself, when it's coupled to photons, then the sound speed is basically the speed of light, with a factor there. But once it decouples from the photons, then the sound speed roughly basically becomes the ordinary sound speed for an ideal gas, non-relativistic. So this is the part that I wanted to emphasize here. So you have the Jeans scale. So this is a plot that shows the size of the perturbation in the comoving frame as a function of time. And I will not talk even about the first part. This is when radiation dominates, roughly at this redshift. I really want to concentrate about the second part. So the Jeans, the solid line that you see here, the white line, separates these two behaviors, acoustic and unstable growth. So it doesn't matter how much, it doesn't really matter the behavior with A, but something happens at the time of the coupling. Something happens at the time of the CMB, because suddenly the photons decouple, and then the sound speed of the fluid is no longer the speed of light, because it's not radiation pressure that is driving the oscillations anymore. Now it's just the ordinary sound speed of an ideal gas, non-relativistic. So you have this sudden, very sudden drop in pressure support. So this line, this division, the Jeans scale drops by many orders of magnitude, by like 10 orders of magnitude in Jeans mass. Now this is important because just before the coupling, this Jeans scale corresponds basically to the size of clusters, and just after the coupling, it becomes tiny. So in principle, all perturbations above this, so this is 10 to the 5 solar masses, can grow. In principle, after the coupling, so after the time of the CMB, you still have the oscillations, but they just happen at a very small scales when it comes to very small masses. And as you see, it actually continues dropping. So more and more perturbations can start growing because of this. And the key is this sudden drop. Okay. Now the last part of physics that I want to talk about in baryonic perturbations. So all of this has to do with acoustic oscillations. That is very important is this silk damping that I also described roughly on Monday. And here the idea is that in these equations, in the equations that I described, so in the equation for the perturbations that comes from the Boltzmann equation, there is a part that I didn't consider, which is I didn't consider the interactions between the fluids, so the baryons, and for example the photons, so the interactions between the species. So we are not really considering that, and this coupling, this interaction is not perfect. It's not perfect because it is governed by this Compton scattering, right? So the collisions between electrons and photons. So that gives rise to a mean-free path. This is basically the distance that a photon can travel before colliding with an electron. And you can maybe just imagine that if you have a sea of photons and electrons, then if the distance in the mean-free path is very short, then it means that a photon can quickly hit into electron and another one, and it keeps the photons and the electrons tightly coupled to each other. But as the mean-free path grows, then it means that more and more the photon can travel more and more, a larger distance, and they start decoupling. And with this decoupling, they create this diffusion mechanism because, yes, they decouple, but the few kind of collisions they do into the electrons cause this damping of the fluctuations. Here's more or less what I said. So the photons can diffuse from high density to low density region, decreasing the photon pressure and thus reducing the amplitude of these acoustic waves. So this introduces another scale in the problem, which is the scale at which this mechanism of diffusion is important. And that's called the silk damping scale. I'm not, I'm gonna actually skip here I'm just gonna go here quickly. The silk damping scale just depends on basically this mean-free path and the time of the coupling, as I mentioned also on Monday. So this introduces, I wanted to introduce this because it introduces this scale, so that means a characteristic mass at the time of the coupling, which is around 10 to the 13 solar masses. So what does this mean? It means that perturbations that have it sounds like a very massive, it is a very massive scale, and I'm talking about perturbations, so it sounds strange. But perturbations, remember, is just over the background. So you still can have something basically cosmological, so very, very large, that on average has a density just a little bit more than the average background. So that's what I'm talking about with these perturbations. When you do these calculations, you find out that if there is no dark matter, then roughly all perturbations that are smaller than 10 to the 13 are damped. What does that mean? They are erased completely because of this phenomenon. So they disappear. So if you have perturbations, if you didn't have dark matter, then you would have to explain the formations of galaxies and galaxy clusters in a very different way, because you can only form perturbations that are larger than this scale because of the silk damping mechanism. Okay, so let me stop here. I will check also the time. I have like 40 minutes, so that should be okay, I hope. Let me see if there are some questions. No? Okay, So let me just quickly summarize this physics. So this is the picture that you saw. The takeaway message is that you have this acoustic behavior, unstable behavior of growth, but you also have this damping mechanism. And this damping mechanism is basically what screaming is telling us that there is something wrong if you don't have dark matter. And the thing is that the perturbations basically disappear. Most of the perturbations disappear because of this diffusion of photons that erases the perturbations. Okay. So now let's talk about dark matter. So what happens with perturbations because of dark matter? So why do we need dark matter? I just gave a roughly an idea because of the damping scale, but here's another one. So how can we say from the CMB tell us that there is a certain amount of matter that we need, but structure formation is another proof that we need dark matter, basically cosmological perturbation theory. And this is because we know that galaxies exist at very high redshift. So this is at redshift 10 or so. You can see here some in this image. There are some dots here of galaxies that are confirmed. Some of them certainly confirmed at a redshift of 8, 9, and even 10 or larger. This is when the time the universe was, 0.5 gigayears. There are already galaxies there formed. And if there is a galaxy form, it means that the perturbation has grown a lot, because a galaxy has a density, is clearly an overdense object by a factor of a million or so or more, depends on the galaxy. So we know there should be galaxies by this time. If they are, I don't even need to put here a million. I just know that the delta is going to be larger than 1. Right? Because we know for sure that there's not a perturbation. It's clearly much denser than the average of the universe. So you just have to put this equal to 1, and then just take some of the solutions for the growth of perturbations in the universe at that time, and then you realize that the ratio of the perturbations at the time of the coupling and at the time when the galaxy formed, say at redshift 10, is equal to basically the ratio of the redshifts. So for this example, I'm very super conservative. I know that the delta of the galaxy at the time of the coupling, by making this connection, has to be around 10 to the minus 2. So in other words, the perturbation at the time of the coupling has to be quite large, let's say around 10 to the minus 2, so that at a redshift 10, this is at a redshift of 1000, the time of the emission of the CMB, so that by redshift 10, you get this 10 to the minus 2. You get a growth that is around 1 if you start with 10 to the minus 2. But from the CMB, we have this observation that basically the fluctuations there are around 10 to the minus 5. This factor of 3 is just a detail, but is there a question? No? So from the CMB, we have this 10 to the minus 5. So this is a disagreement. We know that from the CMB that the perturbations were not around 10 to the minus 2, they were around 10 to the minus 5. The perturbations in the baryons, the perturbations in the photon baryon fluid. So we need perturbations in matter that are much larger than that. So if there is no dark matter, you cannot explain this. Okay, so dark matter perturbations, because the equations are essentially the same, then this is exactly the same. Then I can just talk about the same thing. You have the Jeans scale that separate the behavior of the solution into two. But for collisionless system, I cannot talk about sound waves. Right? So there are no acoustic oscillations. They are unstable modes, so the perturbation can grow. But here, there are no collisions. So what happens if the perturbation is very small? It's oscillating, or it's kind of damping. What is happening? What is the role of the Jeans scale when they are very small? Well, when they are very small, this is called free streaming, which you probably have heard, because this is this free streaming scale is important for example, in dark matter particles like WIMPs, for instance. So this free streaming, and I will just describe it quickly. This free streaming is basically, you can see here the details, so I will just say a few words about it. This free streaming damping is basically the fact that if you have a system that is collisionless and you have these random motions, if these random motions exceed the expansion scale, essentially, then it means that particles can move from one point to another one, in a time that is shorter than the age of the universe. And that means that they can essentially escape, because by the time they are feeling the gravitational interaction that's trying to pull them down, the universe has already expanded. So they basically expand together with the expansion. So roughly, this is what is happening. And that means that the perturbations in dark matter are dropped because of that. Okay, so I'm gonna then just summarize what happens for dark matter. Essentially the same picture. You have this Jeans scale that separates the behavior of acoustic, of stability, not acoustic, because there are no sound waves. Then you have this free streaming damping, in which perturbations are completely damped. And then you have the unstable, the growth regime. So what we need for dark matter, for it to work when it comes to the growth of perturbations, is that the free streaming length is much smaller than the case of the galaxies that we see by the time of equality. So we need a free streaming length that is small. And this is, I'm going to skip this because I'm running out of time. This is achieved, for example, for WIMPs, for CDM particles like WIMPs, because they have a free streaming length that is around the Earth mass. So this can be easily achieved. Okay, so I will just summarize and end this part, this plot that I think just illustrates the main points that I have said. If you were to make a plot here of the delta, of the overdensity of a perturbation that is the size of the Milky Way in mass, so 10 to the 12 solar masses, that's the total mass of the Milky Way, including matter and including baryons, ordinary matter, and dark matter. Then what you will have is essentially this evolution. So when the perturbation is it basically becomes is larger than the Jeans scale, it can grow. Then there is this process of acoustic oscillation. So baryons are in blue, dark matter is in solid. Dark matter here doesn't grow, it doesn't oscillate, but it doesn't grow, basically because radiation dominates the background universe. I didn't explain completely this, I didn't have time. Here, dark matter doesn't grow. Then it comes the equality when matter dominates, and then it starts growing. And contrary to matter, that continues to be oscillated, and then oscillating, and eventually suffers from silk damping, so the density drops completely. So this is the big thing that dark matter does for structure formation. By the time of the coupling, you have basically the baryonic perturbations all the way down because of silk damping. So it's completely damped, erased almost. Whereas dark matter doesn't feel that because it doesn't interact with photons. So it has been able to grow much more than baryons. Then baryons just settle again into dark matter perturbations and can form the structures as we know it. So this picture at the end that we have is once you put all the scales together, and you could say, okay, what is the prediction of linear perturbation theory for the initial conditions that is used in the next step, which is the M-body simulations that we will hear about tomorrow. But it is this picture that sets the amplitude of perturbations as a function of a scale. So here is K. Remember these Fourier modes. So very small scales, very large scales. And the prediction is that depending on the scale, you are going to have a different regime of being within the Jeans scale, smaller or larger than the Jeans scale, and the different physics that is going to affect the perturbations. So as I said, for WIMPs, you have this streaming that causes this reduction in the perturbations, but it occurs at very, very small scales. These are scales corresponding to an Earth mass, so galaxy formation occurs at scales that are not affected by this in the CDM model. Okay, so what I will do, if there are no questions, let me stop here for a moment. I have maybe, I believe I have an hour. So I will talk about these other topics that I wanted to discuss, but let me just see if there are general questions about linear perturbation theory. No? Okay, I see no questions. So what I will try to do in this half an hour is give some very short comments about nonlinear, what is called nonlinear structure formation. So this is when you go beyond perturbation theory. So the density was split into this background universe global density, which is given by the Friedman equations, or is related to the Friedman equation, and this perturbation. So linear perturbation theory deals with this delta being smaller than 1, actually around 0.1 or so. Once it grows, you cannot use linear perturbation theory anymore. So it breaks down completely because you cannot use this approach of taking delta much smaller than 1. Mathematically, this means that the equations become coupled across different scales, and this is very complicated to solve. Even numerically, not only analytically, but numerically as well. So the most powerful approach we have to tackle this problem is to use these n-body simulations. And what an n-body simulation does, and it's in its CDM variety, is to take this assumption that the only dark matter interaction that is important is gravity. So it says, okay, I'm going to forget about the particle nature of dark matter, so it doesn't have any interactions at all when it comes to structure formation. So I just set this gravity. And I said that when that's the case, then the equation to use is the Boltzmann equation, this Blasov-Poisson equation that I described earlier. That's completely general, and you should be able to use it always, right? So if you can solve this equation with this being the potential, then you can solve, you know, everything. It doesn't matter that is nonlinear. The problem is that this equation is extremely complicated because it would be this idea of solving this equation, you know, for each point in phase space and in time. So instead, what you do is this average, again, this kind of a statistical average. And this is where the n-body simulation comes about. It changes the phase space distribution. You will hear, I'm sure, much more about this tomorrow. But essentially, the idea is to change the phase space distribution in space. So that's a number of particles in position and momentum with infinite precision, if you want. And it makes like an average and says, instead of talking about that, let me make an average and talk about macro particles, so big chunks in phase space that I'm going to call those simulation particles, and that give me a fair representation of the phase space distribution in larger scales than the scale of these clumps. Right? So this is basically what you do in an n-body simulation. This average representation that is called coarse graining. So you take the prediction from linear perturbation theory for the amplitude of fluctuations as a function of scale, and you make a representation of it, which is called the initial conditions, for an n-body simulation based on this average procedure. You can use linear perturbation theory roughly, it depends on the scale, but roughly at around a redshift of 100 or so. And this is the starting point of most M-body simulations. So you have the CMB give you a constraint on this linear perturbation theory that you have to respect. But once you have that constraint, then you can use perturbation theory until at around redshift 100. And then after that, you make a representation of macro particles, simulation particles, into a supercomputer. And then after that, you just evolve the system. How do you evolve it? It's purely, you are in a co-moving frame. So it's essentially simple Newtonian gravity. The complication, of course, comes from the fact that you are dealing with an enormous amount of particles. Like here, for example, it's 1 billion particles. So the complication is really that, the number of particles, but not the physics. The physics is purely Newtonian gravity. So when you do that, as you will hear tomorrow, then these perturbations, which are by that time around redshift 100, they are probably around 0.1 or less. Then these perturbations can now grow. They are imprinted in the distribution of particles, and then these particles just feel the gravity. And tomorrow, I'm sure you probably are going to see nice movies and pictures and so on. So here I just wanted to show you very quickly what you obtain from these simulations without going into details. As you go as a function of time, gravity starts taking the dark matter. Here you are just seeing dark matter clumping together because of gravity and forming larger and larger clumps of dark matter. So dark matter here doesn't shine, doesn't produce light, but here is represented as purple. You can see there was a question here. It's about the time scale. Okay, so yeah, it says, is it all about post-inflationary regime? So we take initial conditions for body simulations from a specific inflation model. Yeah, so this is a good question. In reality, what you do is anything that inflation has to predict, it has to eventually land into the CMB. So whatever inflation predicts at, whatever inflation predicts has to be consistent with the CMB. So any inflationary model that you have has to be able to explain the observation of the CMB. So for M-body simulations, you don't talk about inflation at all because what you take as initial condition really comes from the constraint of the CMB, which in a way is imprinted in this plot that I put here. So the prediction of this linear perturbation theory has to match the CMB observations. And that means that if there is inflation, whatever modifications into the initial conditions of your linear perturbation equations, then at the end, those have to be constrained to the CMB so that the initial conditions that you put into the simulations are basically a representation or follow from the CMB observations. They are not a representation of precisely the realization, the cosmological realization of the CMB, because we live in a different universe. They are a random representation of those statistics. By statistics in the matter, I just mean this shape. So smaller scales are denser on average than larger scales because of this prediction of the theory. Here are actually the acoustic oscillations and so on. So all of that has to match, it has to agree with the CMB. So inflation is something that is constrained by the CMB, not by M-body simulations. Another question is about dark energy. If the simulations consider a dark energy, or is it not necessary? Yes, some simulations consider dark energy. Anything that can change. So let me say something about this because I don't think I mentioned it. So the simulations work in the co-moving frame. So the computational box that you create is in co-moving coordinates. The expansion of the universe enters just in the scale factor. So if you have something that affects the expansion of the universe, like a dark energy model, then it's going to enter indirectly into the equations that you solve in the comoving frame, because the equations that you solve in the comoving frame will have some impact because of this H. So this is the way I know that dark energy models that are different than the cosmological constant enter into simulations. Not directly into the equations of motion, but indirectly into the equation for the scale factor. Just check time. I think I'm more or less fine in time, so I'll try not to rush too much here. So this is one of the biggest successes of simulation, and is really the, I suppose, it should be highlighted as the one of the big successes of the lambda CDM model. So what you see here is a picture. Well, it's two things actually. One is the result of basically all the knowledge on structure formation theory, taking the initial conditions from the CMB, using linear perturbation theory, and then using n-body simulations to populate the universe, or to create a simulated universe today. So create this cosmic web structure around us, virtual, so it's not around us, sorry, a virtual cosmic web structure. And in each of these blue kind of points that you see here, or not points, but spheres, roughly spheres, each of those represents, or it's the place where a galaxy is supposed to form. So then you can populate in a educated way, you populate these dark matter halos, as they are called, by galaxies, and then you see how they are distributed in your simulated universe. You see how the distribution of galaxies here in this simulated universe. So you can make a virtual observation of what an observer in this simulation will see around it today. And this is what you will see. And you can actually mimic a survey, a real survey. So the kind of the patch of the angular sky that they cover, and how deep they reach in redshift and so on. And this is what they did here with what is called, very famous simulation called the Millennium Simulation. All of this part below is the result from this virtual universe, whereas the part above is the result from real observation. And here they kind of did it on purpose, so that you see that there are similar structures here and here in the simulated universe and in reality. Like the large scale structure of the universe looks basically the same statistically, right? This does not have the initial conditions of our universe. It has a random realization, but statistically is the same as this one. So this is the big success of the lambda CDM model, to match the large scale structure of the universe. What else can we get from the simulations? We know the presence from these simulations. We can study all the way to the nonlinear regime. So all the way to the formation of these very dense objects that are called dark matter halos, which are systems in equilibrium. This is a collisionless system. So gravity starts collapsing the perturbation. So what happens? The perturbation becomes infinitely large? No, because eventually the random motion between the particles stabilizes the system into virial equilibrium. So again, this game in which the expansion of the universe doesn't play anymore a role, because you are in this self-contained unit, which is held by gravity and random motions. This is what a dark matter halo is, one of these blue objects that I mentioned earlier. See, there is a question here. The question is, what parameters are compared to see if the simulation is working or not? So how do we know the simulation is working? Except for looking at the visible points, visible clumps that I showed in the previous picture, and how are these in general? So Thanks. This is a great question. So this is related to this. Yeah, here is all visual, and I just gave a visual representation. So what you can do to do this properly is to take basically to compute the power spectrum, or the correlation function is called. So what is this? Is basically this, essentially this. So you just count the number of for objects. So you count the number of galaxies. So you have here the reality, right? So you count the number of galaxies as a function of scale. So I take an angular scale, like you do with the CMB, but you do it with galaxies. You take an angle in the sky, and make an average of how many galaxies over the random distribution I get as a function of a scale. And that gives you a correlation function, a degree of the amount of clustering as a function of a scale. So that's a statistic that you can get, a 2-point statistics that you can get from observations. And then you can take that statistic measure and compare it with what the simulations predict. And it's an excellent match. That's one of them. And then I think that was related to the question. There are many other things you can do. How good are these? They are excellent. So I think there is no doubt that when it comes to large-scale structure, there are no major or significant or controversial disagreements with the predictions of lambda CDM. Of course, within the errors of the observations, could there be new physics? Could there be something more interesting? Could it be deviations over lambda or of CDM? Yes, but not within the observations, the current precision measurements we have now. Okay, so this is not the whole story, and you will hear a lot about embodied simulations, I'm sure, tomorrow. This is not the whole story because I just talk about dark matter. At the beginning, in the first hour of the talk or so, I was talking about. Let me just check the time. I believe I have. I was thinking I have 2 hours, but of course not. I have like 15 minutes, so let's stay within time. So I was talking about dark matter and baryons, right? And then I stopped talking about baryons and I just talk about dark matter embodied simulations, collisionless systems. So what do you do with baryons? Well, of course, baryons are much more complicated. Sorry, they become more complicated because it's no longer just a fluid, but it has all these additional physics that make it more and more complicated. So you don't only have to deal with the hydrodynamics of the fluid, but you have to start dealing with, okay, how stars form, how stars explode and inject material into the environment, and so on and so on. So there is a whole complex array of physics that you have to deal with to go from this picture of embodied pure dark matter to actually form galaxies. And this is something that Annalisa is gonna talk about in a couple of days, or tomorrow, I believe. Yes, after Gustavo. So this is all, of course, a very complex phenomena of actually explaining galaxies. And as you will hear from Annalisa, I think there's also been an incredible progress in this field of actually putting galaxies and taking the predictions of the lambda CDM model and adding this extra component that is crucial, which is the physics, this complex physics of baryons. So you take these initial conditions of the CMB, you did the simulations, you assume that gravity is the only interaction that matters for dark matter, and then you add all these complications that you will hear about tomorrow. You do this, and then you find something, you have a complete model for the formation and evolution of galaxies, in principle. By complete, I don't mean that is not a complete theory because of the reasons I explained. We don't know what dark matter is. We don't know what the cosmological constant is. We also do not or cannot resolve all of these processes, all the physics of all of these processes. It's all done in an average way, as you will hear tomorrow. So there are lots of still unresolved issues in this part as well. But it's still impressive that you can, at the end, form in a virtual universe simulated galaxies such as this from the Illustris project that you will hear about tomorrow. So this will complete this picture of, I think, really what would be the ultimate goal of a structure formation theory, which is explain completely how galaxies form and evolve. And it needs as a backbone something that looks like the lambda CDM model of a structure formation. So I just want to close in the last 10 minutes or so. I just want to close by precisely saying the limitations, or not limitations, but the possibilities for going beyond this lambda CDM model when it comes to structure formation. And really, this is related to answering this question, which hasn't been answered, but it's a hypothesis of the lambda CDM model, which is gravity the only dark matter interaction that is important for the physics of galaxies? This is something that is not in the CMB. This is something that is not in the large scale structure. All the observations we have not been able to answer this question. Okay, so this is why it's a fundamental question. We might not discover what dark matter is or the cosmological constant in the next 10 or 100 or 1,000 years, but I'm very interested in this question because I think this is a question we can answer within our lifetime to finally settle whether lambda CDM model is the structure formation theory. So this is again related to these very important questions that, we don't know what dark matter is. We don't know what kind of particles, how it interacts, and this is a lot of the topic in this school is precisely to try to find out what kind of the particle nature of dark matter. And just to emphasize, there is nothing, there is no indisputable evidence that there is something wrong about the CDM hypothesis. But there are very reasonable alternatives to consider. So that's what I want to talk in the last minutes, just to give you a flavor that CDM is not the end of the road completely, or not, at least not yet. So we know that there is this incomplete. There are many theories for the particle nature of dark matter. So this is just an incomplete set of this, trying to describe. We'll try to describe this in the language of particle physics. So this is adapted from this paper. In particle physics, when you talk about the nature of a particle, well, you talk about certain fundamental properties of that particle, and these two are perhaps the most fundamental, or at least to me, that I'm not a particle physicist: the mass and the interaction. This is interaction when it comes to the mechanism of dark matter production. So, for example, as you have heard, this freeze-out mechanism and weak scale type of mechanism of interaction give rise to, for example, supersymmetric particles. The weak scale, you could have stronger type of interactions like in asymmetric dark matter, or you can have sterile neutrinos, gravitinos, things that have to do with fuzzy dark matter. This is action-like particles and so on. So you have all these possibilities, and of course, also the possibility that dark matter is purely interacting gravitationally, like this. Now, as an astrophysicist, we are more interested in this kind of parameter space, in which you talk about not the mass and the interaction, but you talk about the scales. So you talk about the scales of interactions, so scattering rates, basically, and scales of interactions for having these different initial conditions after the CMB that remain unconstrained, which I will describe more and more. It's essentially having a mechanism that constrains the formation of galaxies at certain scales. So CDM would occupy this big chunk and basically say, well, forget about galaxies, because CDM cannot tell you, cannot give you, or by construction is not going to give you a cutoff, or is not going to influence the formation of galaxies because of its nature. So it doesn't answer the question about the nature of dark matter, because by construction, it puts that nature at scales that galaxies cannot probe. But there are other models, like warm dark matter, for example, as very well known, in which you have that scale affecting the scale of galaxies. So the nature of the particle affects the scale of galaxies. Or you have models like self-interacting dark matter, in which the particles can collide with themselves, and they, in this case, the scattering rate becomes very large, and they affect the evolution of dark matter, because you have suddenly these collisions, and by affecting the evolution of dark matter, they affect the evolution of how galaxies form. So this idea that in structure formation theory, we have, or galaxy formation theory, we have a few unresolved questions, and I think these are critical. So what is the minimum scale for galaxies to form? So if someone asks you, what is the minimum mass that a galaxy can have, and why it has that minimum mass, well, maybe there will be some discussion of what is the minimum mass it can have, but nobody can answer to you fairly what is the minimum mass that a galaxy can have, because this in principle remains an open question. It depends on whether the dark matter nature impacts this minimum scale or not. And the same about this. What is really that sets the dynamics internally of the galaxy? Again, there are many physical mechanisms we know of, but there are also mechanisms related to the particle nature of dark matter that remain unconstrained and could actually affect this question. So I just want to take the last 5 minutes to talk about them. I will just close with that. Sorry. So one possibility is to have this question of whether if dark matter physics can basically affect the minimum scale. So it can determine what is the minimum mass that galaxies can have? And the answer is yes. One way is with introducing this free streaming damping. Remember that I talked to you about this free streaming damping that says, okay, galaxies cannot form beyond certain scale because free streaming damping is a problem. That's open, and that's called warm dark matter. But you could also have new forces between the dark matter particles that create, basically you have extra fields, extra particles that create radiation pressure in the same way as the photons and baryons create acoustic oscillations, and you have photons exerting radiation pressure on baryons. You could have dark photons exerting radiation pressure on dark matter to create this acoustic oscillation. It's completely possible. There are particle scenarios that consider this, and it's allowed by the data. So you have a situation such as this, in which you have the CDM, the lambda CDM prediction, but beyond this scale, which is the scale of dwarf galaxies, this is largely unconstrained. So you could have anything. So here is the constraints from the CMB, other type of constraints come here, but after this point, roughly the scale of dwarf galaxies, this could be, this is basically unknown. We don't know from observations how this is supposed to be. So you could have the CDM that goes basically all the way until the, for example, the WIMP scale for a cutoff, or if it's this purely gravity, something that doesn't interact with anything else, then it just continues going and going. Or you could have these two types of oscillations or the free streaming damping. The last possibility, or the other possibility I wanted to talk about, because I work a lot on this, is self-interacting dark matter. So here you also have the possibility that particles can collide with themselves. So you can no longer use the collisionless Boltzmann equation, because in this case, you have the possibility of dark matter colliding with each other, again, with some kind of force. For example, it could be the same dark photon mediating these interactions between the dark matter particles, a kind of a Yukawa type of potential. Is the cross-section as a function of velocity, so that you have a large cross-section at small scales, and a small cross-section at larger scales to avoid the constraints that we know of. And just by having, it's not a lot of collisions. I mean, sometimes when we talk about this cross-section, it seems large, but of course it's not the cross-sections for the gas and the baryons. This is just around 1 scatter per particle in the age of the universe. So if you look at a given dark matter particle in average, in SIDM, how many times it has collided in the age of the universe, well, just 1. But that's enough, because it's an average, that's enough to change dramatically the predictions of these theories. So I will just close with this picture here. I think it's kind of the state of where we are. It summarizes this nicely, I think. When it comes to the power spectrum, so again, this amplitude of fluctuations as a function of scale, this is just it's not like a formal constraint, but you can take this area to be constrained to be CDM. You cannot have strong deviations here, because then you have problems with observations. But at smaller scales, and this is precisely the scales where the smallest galaxies live, you can have all kinds of stuff that remains unconstrained. When it comes to the possibility of having collisions, so this would give constraints on new, for example, either new forces on the dark sector, or the possibility of physical mechanisms like free streaming damping in the case of warm dark matter. You could also have interactions between the particles themselves. So this would give you a constraint on, again, these dark forces, but kind of indirectly through the effect of these collisions in the evolutions, in the dynamics of galaxies. And again, if you go very low in cross section, then it doesn't matter, because it basically behaves as collisionless. If you have very high, then you have other problems that I'm going to discuss about. And again, the smaller galaxies, the constraints you have here from other observations, you cannot have very large cross sections here, because you run into trouble. So you have basically this window here in which you can have this possibility. So I think it's very important to have these additional parameters, because they kind of have a key, or could have a key role in the physics of galaxies. Okay, so that's it. I think I would just put this slide and close there. And thank you very much. And I will just stop and take questions. Yeah, I see a question here. So the question is, if this work structure formation, let me actually go back to that point. The question is if we can relate these works of structure formation to matter-antimatter asymmetry. So the matter-antimatter asymmetry is an issue of the early universe. So, just to say to everyone, this is the fact that we know in the universe there is much more matter than antimatter, and this is something that is dealt with here with baryogenesis in the early universe, so models that explain that matter-antimatter asymmetry. Now, when it comes to structure formation, so this happens sufficiently early in the universe, so you have this mechanism of asymmetry, and that's it. It has no impact, as far as I'm aware of, at any scales on structure formation. But this principle, this idea of matter-antimatter asymmetry, can to some extent motivate the idea that dark matter should also share that asymmetry. And this is these models of asymmetric dark matter, in which the dark matter, for example, in the standard picture of WIMPs as having this mechanism of freeze-out production and so on, in which you have the same amount of dark matter and anti-dark matter. So the dark matter is its own antiparticle. In this standard picture, then you have the same amounts, right, of matter and anti-dark matter. In these other models of asymmetric dark matter, you take as a principle that dark matter has to be asymmetric. And then you have another mechanism to production, or basically you have this asymmetry that allows you to have larger cross sections at the beginning. And that, as I said, partially motivates these models of asymmetric dark matter that has consequences for structure formation, because some of the self-interacting dark matter models here are related to that. But this is very, I'm describing this in a very rough way, okay? So I hope that's related to what you were asking. Okay, let me see, that's another question. The question is, while modified gravity theories are not much considered, is there any possibility that simulations of these theories may also generate this large-scale structure? Yeah, so this is a very good question. So modified gravity, the way it's not my field, so I hope I'm not making a mistake here by saying this, but I typically, for what I know, they are divided in two. So, or I would divide them in two. So there is the modified gravity that deals with models of dark energy. So there is the modified gravity theories that deal with that, and that's usually very large scales. And so deviations of, for example, the expansion rate of the universe and so on, that are based on modified gravity theory. I don't know if they have a different prediction when it comes to the actual clustering of matter, because as far as I'm aware of, usually they look at the impact of the background universe, but perhaps they also have relevance for structure formation at very large scales that I'm not aware of. Then there is the second type of modified gravity theories that try to basically get rid of dark matter by saying that dark matter doesn't exist, and instead what is wrong is our theory of gravity at galactic and supragalactic scales. So basically they modify, and there are different versions of these theories. As far as I know, there is no fully consistent relativistic theory of modified gravity, but I haven't followed the recent developments. Maybe there is something new there, I'm not sure. So it has some theoretical problems because of that I'm aware of. And then it has other problems with explaining certain observations like this one, which is the bullet cluster. It has some problems to explain the properties of the CMB fully, and another bunch of problems. It explains very nicely rotation curves and other observations at the level or sometimes even better than CDM. But because it has all these different problems, this is why it remains not as successful as CDM. Although I guess some people might say that the reason it's not as successful is because as a community, as a scientific community, we haven't invested as much in developing that theory, so it still needs to be developed, modified gravity, when it comes to dark matter. But I think, at least my perspective is that it remains having some serious problems at the level even of structure formation in the early universe. So until those problems are really solved, I don't think we can talk about it in the same level as lambda CDM.
Okay, so thank you, Jesus, and also to all the participants for their questions and comments. So if there are no further questions, I will stop this live stream here.